All right, so in this part, we're going to begin with a high level overview of hypervisor technology. Um, we're going to examine some of the internals of hypervisors. We're going to look at actual examples, reverse engineer some of the hypervisor code from Microsoft, and we're going to look at KVM on Linux and things like that. As we go on to the next sections, we'll go into other parts such as more details into the other low level parts of it, how it communicates with guests and hosts, isolation, um, EPT, nested paging, AMD and Intel differences. We're going to write a custom little Rust based OS to trigger some functionality in a hypervisor and capture that in an emulator and walk through how that can be leveraged for fuzzing. And then we're actually going to reproduce a bug from a hypervisor. I haven't decided which yet. Could be KVM or Microsoft. We'll see. We'll read up on the bug, reverse out the bug if needed, and we'll write a POC in our little custom OS that triggers it. There'll be other things we'll go through as well, but just to begin with, we're going to walk through what is a hypervisor really and kind of get comfortable with how it actually works. Now, what I have up here, we're not actually going to go through much because it's so um, condensed, I guess. It's a lot of information, very dense information. And this is from the Software Developers Manual from Intel. So you can download this from just Intel website. It's the SDM. And that contains a lot of things about Intel processors. One of those you see chapter 24 here is Introduction to Virtual Machine Extensions. This is where if you wanted to write your own hypervisor or just kind of understand hypervisors yourself looking through a manual, you can. Hypervisor technology is documented in, Intel's got their own version of hypervisor technology, and that's in the Intel manual. AMD's got their own, ARM64 has theirs, depending on, and it can differ depending on what CPU model you're assessing, because there's lots of extra extensions and features that get added on or removed depending on the CPU model. But for example, if you wanted to write a hypervisor, you'd be diving a lot into these manuals. So I just make that known as a resource if you wanted extra information on some things. It's not that easy to understand if you haven't worked with it before, but it's there. So when it comes to hypervisors, right? I just got some named here. HVIX64, for example. This is the Intel hypervisor on Windows, and this is normally at System32 HVIX64.exe. Guess I don't need that part. Same with the AMD version, which is HVAX, and then the ARM64 version. But you probably won't have the ARM64 version on your machine unless you're running a laptop, like a Surface or something, or one of the ARM surfaces. While the Intel and AMD hypervisors will likely be on any x86 64 Windows. But the main idea, right, is first of all, why are they even used? Well, you'd have a hypervisor, right? Can be anything. There's a few reasons why they're used commercially. They're typically for isolation, right? Like when you have a cloud instance running, you'll have multiple OSs, OS 1, 2, blah, blah, blah. And they all going to run on the same physical machine. So let me put that in. Let me send that back up here. I want to say that this is a physical machine, right? Without a hypervisor, a physical machine would mostly just be OS 1 and that's it. You'd be running Windows or Linux or something. You can boot into different OSs if you have different, hard drives with an OS on each one or whatnot. But at any single point in time, you're pretty much only one operating system owns the hardware of a physical machine. With a hypervisor, you got a little bit of isolation here. So, oh, not that far back. Um, Okay. You'd have it like this. So this is isolated, this little second box. And the reason for that is there's hardware, right? A physical machine has hardware. Maybe I need to extend this out a bit more. And let's add in that hardware line. Oops, wrong one. Rectangle. So this is the actual hardware. So hardware is like, your graphics card, your sound card, your hard drive controllers, and your RAM and everything like that. If you wanted to run two operating systems, right, they can't both be fighting for RAM because then they just clobber each other's memory. They can't both be trying to output to the screen at the same time because your screen will just be seeing mangled garbage, right? That's why historically, without a hypervisor, there's only one operating system running at one point in time because an operating system owns the hardware, right? It controls the graphics, the sound, and all those sort of low level physical things. And if two operating systems trying to output different sounds, different graphics, try to handling keyboard input at the same time, it won't work. So instead, there's an isolation layer where hardware is only owned by the hypervisor. The operating systems, they don't own hardware. Hypervisor owns hardware. If the OSs want to interact with hardware, like they want to write something to the screen, produce a sound, that goes to the hypervisor. I need to bring this one to the front and this. There we go. They go to the hypervisor. And then the hypervisor will handle how it interacts with hardware. So for example, on Windows or on a desktop OS, right? Linux, Windows, Mac, if you're running Parallels, if you're running VMware or Hyper-V, the graphics, like the display that you would see from the VM is in a window, right? It's in like a little window, just like your web browser window or something. And anytime the OS in that VM wants to write to the screen, the hypervisor will write it into that Windows screen, right? So any graphics that OS is running will be displayed on that Windows screen. And that's there because the hypervisor intercepts and handles talking to hardware on behalf of the OS. The OS doesn't directly speak to hardware. Now, there are some ways to pass through hardware to an OS. Typically, that's called pass-through, right? Or like direct pass-through or something like that, where you take a chunk of hardware and you dedicate it to an OS, such as, maybe this is GPU2. It's my second graphics card that I got plugged in. And I'm going to say this is owned by OS1. So OS1 can use GPU2 all to itself. That means nothing else, the hypervisor nor the OS2 can use GPU2. Only OS1 can use GPU2. The reason why you do this is maybe you have a VM, but you want that VM to do very graphically intensive things that it would benefit from not having to go through a hypervisor. It would benefit from having direct access to the graphics card. So then you just say the OS owns, that hardware. And that's entirely fine. It just means nothing else can use it. But typically, most of the hardware, if not all of it, is just abstracted away, and the OSs are forced to go through a hypervisor to interact with hardware. Now, the question you might have is, how does an OS know to go through a hypervisor, right? And the thing is, it doesn't. So hypervisors are supported by hardware. So the CPU itself has to provide mechanisms for a hypervisor to run. In this case, one of the mechanisms is intercepts, where when you're running a VM, if that VM goes to do certain operations, the CPU will pause execution of that CPU core and switch that core to running in the hypervisor. And it'll provide the hypervisor certain information as to why it switched out from OS1. So if OS1 goes to talk to a graphics driver, As soon as it goes to read or write to that GPU, it would be intercepted and it will go to the hypervisor. And the hypervisor will be given information from the CPU. It'll be told, this VM tried to access this address, and then you'd see that that address belongs to GPU 1 or belongs to the sound card, and it tried to read or write this data. The hypervisor can then act on behalf of OS 1, interact with hardware as it needs to, and then return out to OS 1 and continue execution in the guest. So it's not so much that the OS knows it's under a hypervisor, it may never know that it's under a hypervisor. It's more that the CPU itself handles this intercept, this notifying of the hypervisor when the OS is trying to interact with something that belongs to the hypervisor and not the OS. Some of these intercepts are configurable. You don't have to intercept on everything, and you can pick and choose what to intercept on. That's up to the hypervisor and also which particular model of CPU you're working with to determine what features are present from that CPU, what you can intercept on, what you can't. For example, if you don't have nested paging or extended paging running, the hypervisor code actually lives in the same page tables as the different operating systems, such that OS 1 and OS 2 actually share the same kernel memory space as hypervisor. Now, the trapping still works. It's just that the kernels, the hypervisor's text section and the PE format, the actual binary lives in the same kernel memory, which means it's not protected from being potentially modified by OS 1 or OS 2, which is why they introduced second level address tables, which Intel calls EPT or extended page tables, and AMD is nested page tables. And that allows an extra layer of abstraction when decoding virtual memory, such that the hypervisor's virtual memory is completely separate from OS 1 and OS 2. You can configure it so they don't have access to hypervisor memory, which is how most commercial hypervisors will run. It's how Hyper-V will run. They normally have second level address tables as a strict requirement, but it's not necessarily strict if you're writing your own hypervisor. So that's kind of like how isolation is provided. But this also means when it tries to interact with hardware, hypervisor needs to maintain different states per OS. What I mean by this is, say, what's a good example here of hardware configuration? Maybe one piece of hardware is a serial device, right? Serial device is a piece of hardware, and serial can be configured in certain ways. You could have the IO ports, IO port number of them. They'll have a configurable like speed. They'll have a few other configuration options. But the main point is all hardware, most hardware, a sound card, a graphics card, those sorts of things, will have certain configuration options. And if I grab OS 1 and OS 2, OS 1 might have serial configured in one way, and OS 2 might have it configured in another. Perhaps OS 1 has serial, right? Maybe it's got its own configured speed. It has its own config, and I don't think I need to do that. But the main point is OS 1 and OS 2 have their own configuration for serial. But when it needs to talk to hardware, right, and it goes through Hyper-V, which configuration is it going to use? How can it configure hardware for both OS 1 and OS 2, right? Really, it doesn't. Because if OS 1 wants to talk to serial under one set configuration and OS 2 wants to talk to it under a different configuration, then when that goes to Hyper-V, or just any hypervisor in this case, right, just anything, when it goes to interact with serial, or when it goes to do whatever OS1 and OS2 wants to do with serial, it has to handle the fact that they have different configurations. So what it does is it emulates it. The hypervisor will have what's called a VDEV, or a virtual device. And a virtual device is just complete emulation of an existing of a hardware thing. So, for example, it might have emulated serial, and that would have, IO port, speed, associated VM, blah 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 blah, or some stuff like that, right? It would emulate hardware, and or it can para-virtualize hardware. There's two different things it can do. It can para-virtualize hardware or completely emulate hardware. With complete emulation, Hypervisor doesn't even need to talk to a real serial. Instead, when OS2 or OS1 goes to talk to what it thinks is real serial, it'll actually trap to the hypervisor, and the hypervisor just completely emulates it. It emulates whatever OS1 and OS2 tried to do with hardware, handles the responses in that just through emulation. Think of other emulators like QEMU or Box. They do the same thing, right? They do full emulation. But you don't need to do full emulation. You can do power virtualization, which means that the OSs themselves have a special driver installed that knows that it's running under a hypervisor, and the driver is responsible for talking to the hypervisor in order to do certain things in a more performant manner. We'll examine that more a bit later. Also, even with emulated things, for example, OS1 and OS2, it may still interact with hardware in the sense that maybe OS1 is trying to do something with serial. That goes to Hyper-V, which will, based on its serial emulation for that OS, determine what the output should be. And if that VM is configured such that whenever it goes to do something to serial, we pass through the output to actual hardware serial, then we'll pass on the emulated output to hardware serial. By this, I mean, we don't have to worry about configuring speed and stuff, right? If OS1 is trying to print off a string to serial, like it's trying to print the string hello over serial, right? It'll have its own emulated serial that's configured with whatever speed and stuff that the OS1 has configured it with, and it wants to send hello over that serial. Now, if that VM is configured such that all the serial writes it does goes to actual hardware serial over some other port and speed, Hypervisor will get this message. Based on the emulated serial, it'll determine the output. Maybe it'll say, okay, the output really is just passing through the string hello. So it's going to go through and pass through the string hello to its own hardware serial. But note that the hardware serial's configuration, like the speed and stuff, does not have to match the configuration of OS1. All it needs to do is pass through the string hello, which is the expected output of it. The configuration that is completely irrelevant, which is why it's still kept isolated from OS1 or OS2. Another example of this is the network, right? Say this is network, like TCP/IP. TCP/IP will have a whole bunch of configuration things associated with it. And now if OS1 or OS2 wants to send something over the network, we would have some sort of emulated NIC, or some sort of just virtual NIC that handles receiving the network requests from OS1 and OS2 and doing whatever it needs to do with it. If that needs to go over the actual hardware network interface card to reach out to the internet or something, it will. But the network interface card on hardware will be configured completely separately to OS1 and OS2. In fact, you can tell OS1 that you're using a VNIC off like an E1000 network interface card and you just emulate that E1000 network interface card when your actual network interface card is something completely different, right? I'm not going to put any other model. Maybe it's E1000E or something. Like, it doesn't matter. It'll take whatever it's expecting to send and receive and format it appropriately for the actual hardware it's talking to. That's how that can work. Now, think of the case of, I'll do a quick example of emulated versus paravirtualized. Emulated versus paravirtualized. Okay. So let's continue with the example of a NIC. You have a NIC, right? When a VM wants to send data to it, say a VM has 20 packets and it writes each packet one by one to the NIC. And say this is like a guest, right? The guest VM wants to send 20 packets over the network, so it writes each packet one by one to its NIC. But this is a VM, so every single write to the NIC is actually going to be trapped, and that's going to be sent to the hypervisor, which means when it writes the first packet, it'll trap to the hypervisor. Writes the second one, traps to the hypervisor. Third one, traps to the hypervisor. Now you can see that there's going to be latency here. And the latency is because every single packet write is trapping to the hypervisor. And that's not a fast operation, right? The CPU has to flush caches, switch memory space. Then you have to go to the hypervisor. The hypervisor has to decode why the trap happened, and then it has to handle it. And if we're sending 20 packets one by one, it's going to trap like 20 times at least to do that. Now, for performance, they introduced the concept of paravirtualization instead. Paravirtualization is, in this case, instead of writing each packet one by one, maybe we batch write them. But we can't batch write them to the NIC because the NIC only supports one by one, right? So instead, this goes to a special driver, maybe a VNIC driver. And the VNIC driver has a special communication mechanism with the Hyper-V that says batch write 20 VNIC packets to Hyper-V. So in this case, the driver sets up a special communication channel with the hypervisor, and when it goes to write, say, 20 packets, it writes those 20 packets over the special communication mechanism to the hypervisor, and that's only one intercept. So instead of 20 intercepts happening in the first case, in the second case, only one intercept happens for those 20 packets. The main difference, well, there's actually quite a few differences, but I mean, one of the main ones is that this first one, the OS doesn't need to know it's running under a hypervisor. It just does what it does when there's a hypervisor or there's no hypervisor, which is writing to the NIC. In this second case, there's a special driver that lives in OS1, right? And that driver knows that it's running under a particular hypervisor. So when the OS goes to write those packets, it intercepts that and it goes, wait, I know I'm running under a hypervisor. I have this special communication mechanism set up with the hypervisor. I'm just going to tell the hypervisor to write these 20, NIC packets, whatever, over my special mechanism. So this requires the existence of a driver that knows it's running under a hypervisor to run in the OS. Okay, so you'll see it on a VM. If you spawn a Gen 2 Windows VM and you look at the running processes, you'll see some virtualization related processes running because Gen 2 VMs utilize paravirtualization a lot. They'll have drivers in them that know they're running under hypervisor. if you run a Gen 1 Windows VM, I don't think you would have most of those virtualizations there, most of those power virtualizations there, because Gen 1 is mostly fully emulated. Um, Same with like VMware, right? With VMware, you can install VMware tools, and there'll be other components installed in that guest VM that allows it to communicate out to the host, which is why once you install VM tools on a VMware guest, you can copy and paste, but just control Ving into the VM window, because there's components in the guest now, thanks to VMware tools, that can handle talking to the hypervisor and knowing that it's running under a hypervisor. Without VM tools, you won't have that capability. That's kind of how that works. So now we kind of got a roughly high level knowledge of, isolation is provided by the CPU being able to intercept when a guest does certain things. We know that you have full emulation, and then you've also got power virtualization, which both methods, there can be different attack surfaces in hypervisors, right? Because in both cases, a hypervisor is passing input from a guest. When the guest traps to the hypervisor is passing the packets that we were going to write to the NIC. That's an attack surface. In power virtualization, you've got the VNIC that's doing some initial passing. And then when that writes it to the hypervisor, you got other parts of the hypervisor that's doing passing. So more different attack surface. But we'll continue on next, looking more into some of the lower level details by examining hypervisor code of both source code, from like Linux KVM, but also reverse engineering Hyper-V and things like that a little bit, to see more about the implementation in code and how that matches our kind of high level understanding at this point. And then we'll continue from there.